Guys, sorry about that. There's just a lot of stuff going on in the hallway apparently tonight. I don't really know what's going on. Okay, so we said that the net force is just something that, or the net force is the vector sum of all forces acting on an object. So if the net force is 0, then that means that my object will not be undergoing an acceleration. If the net force is not 0, then that means that I'm going to have some type of velocity change, which means that that object will be accelerating. There are a couple of categories of forces. One category of a force is called a contact force. So we have 3 examples of contact force here. I may be grabbing a spring and pulling on that spring. Maybe I'm taking Ella on a little wagon ride. Or maybe we have Matt or Logan kicking a football up in the air to make that field goal. So these are all examples of contact forces. And a contact force is a force that involves physical contact between 2 objects. So there actually has to be objects touching here for that force, for the contact force to be applied. We have a second type of force, which is called a field force. And a field force, it also has another name, which we'll hear at a distance forces. So we can call these field forces, or we could call these at a distance forces. And field forces do not involve physical contact between objects. Instead, a field force is going to act through space, or act through empty space. Examples of this could be gravitational force, which would be between 2 masses. I could have an electric force, which would be between charged particles. I could also have some type of magnetic force, which would be between 2 types of something with magnetic strength. So in this case, I have a magnet that would be attracting iron. So 2 categories of forces: contact forces, field forces. Contact, I have to have physical contact between the 2 objects. Field forces are going to be, or at a distance forces, are where I have that force acting through empty space. Okay, so let's just talk about net force. So for example, I have a box here and I have 2 forces that are being applied. So I have a guy pulling the box from this end, a guy pulling this box or this crate from the other end. So because I have these vectors, my force vectors here, and they're acting, it looks like they have equal magnitude, but they're acting in opposite directions, then the sum of these forces total will give me my net force. So in this case, if I'm looking here, equal magnitude but opposite direction, I'm going to do the net force of, let's say, F2 plus F1, but since F1 is acting in the opposite direction of F2, F1 is considered to be moving in that negative direction. So I would say the net force is going to be F2 plus a negative F1 because it's going in that opposite direction. So that would give me a net force of 0. So this crate, this box, will remain motionless. It's just going to sit there. It's not going to move. It won't have an acceleration since the forces are acting in equal in magnitude but opposite in direction. Now let's say that this guy starts to pull with a stronger force or a larger force than this guy over here. So I can see that F2 would have a larger magnitude than F1 does. And if F2 has that larger magnitude, then I'm going to get some type of acceleration. And that acceleration is going to be in the direction of the force that has the larger magnitude. So I can see it would be accelerating this way. So my net force, when it's not 0, I have unbalanced forces, then that's when I'm going to get an acceleration. Now, the name of the diagram where I draw arrows representing the forces that are acting on an object, those are called free body diagrams. And that's what we're going to be drawing a lot of in this chapter especially. And not all of the forces are actually shown that are acting on this crate right now. But for right now, we just want to look at a simplified version of a free body diagram. So we'll get more into free body diagramming when we start talking about Newton's second law. Okay. Okay, we also, of course, have the vector nature of force. So just like in the last one, it could be as simple as, let's say in this first case, I have a force that I've applied to a spring, and a spring is a really easy way that we can calibrate magnitude of force. But let's just say that in my first case, I've applied some force, and I can see that this force will elongate the spring at 1 centimeter. So let's say then that I have a different spring, and I apply a larger force. I can see that this force would elongate the spring 2 centimeters. If I apply both of those forces together, I apply the first force and the second force, I can see then that since they're acting in the same direction, I'm going to add those two force vectors together, and in this case it elongates the spring by 3 centimeters. But what happens if I apply a force at some angle? If I'm applying the force at some angle, we're going to need to think about the forces in components. So if I have a force that's at an angle, I need to think about how that force is acting in the x direction and how that force is acting in the y direction. So if we have that force at an angle, we will have to break it down into components. And we should be kind of used to that based on our projectile motion stuff. Okay, so let's say that we have a book lying at rest on a table. The book will remain there at rest because A, there is a net force, but the book has too much inertia. B, there are no forces acting on the book at all. C, it does move, but it's just too slow that we can see it. D, there is no net force on the book. Or E, there is a net force, but the book is too heavy to move. If the book is at rest, and the book remains there at rest, it is because D, there is no net force acting on the book. There are forces that are acting on the book. I have gravitational force that would be accelerating that book towards the center of the earth, but I also have, if the book is lying on the table, I also have the table pushing back up on the book. So if it's at rest, the net force, or the sum of all forces that are acting on that book, must be 0, which is the reason why it's not accelerating. Okay, let's say that a hockey puck slides on ice at constant velocity. What is the net force acting on the puck? Is it A, more than its weight, B, equal to its weight, C, less than its weight but more than 0, D, it depends on the speed of the puck, or E, 0? In this case, my answer would be E, 0, because of that key phrase that says constant velocity. If a hockey puck is sliding at constant velocity, the speed isn't changing, and my direction may not be changing, then I can't be accelerating, because in acceleration I have to have a change in velocity. So since it's moving at constant velocity, then that means that I have no acceleration, so the net force acting on the puck must be 0. Okay, on this next question it says, you kick a smooth flat stone out on a frozen pond, the stone slows down, and then will eventually stop. You must conclude that A, the force pushing the stone forward finally stopped pushing on it, B, no net force acted on the stone, C, a net force acted on it all the way along, D, the stone simply ran out of steam, or E, the stone has a natural tendency to be at rest. Okay, so again, the stone slides, it slows down, eventually it stops. So in this case, I would say that a net force acted on it all along. If the stone was first at rest and I've applied some force because I kicked it, I know that since it started to move, it had to have accelerated. And I know that because the stone was at rest, I kicked it, it slides, it slows down. So the fact that it's slowing down means that I still have some type of net force that has to be applied to it. And eventually it stops. So it stops because there's still a net force that is being applied to it. So I have to say that there's a net force that acted on it all the way along. Okay, so in terms of Newton's first law, and then also thinking about the term inertia, before we even get to Newton, long time ago, Aristotle believed that the natural state of objects was to be at rest. And if you got them moving, eventually they would stop again. They would come to rest again. So Aristotle believes that everything, every object has this natural tendency to be at rest. We would prefer to be in equilibrium. We would prefer to be at rest. We don't want to be moving at all. But then Galileo comes along, and Galileo does not only some thought experiments, but he also does some experiments in terms of inclined planes. So Galileo does some inclined plane experiments where he's rolling different massed balls up and down these inclined planes, and he realizes in an absence of a force, this object is going to keep moving forever and ever and ever until it comes in contact with something else. So Galileo at first had the inclined plane where he would roll the ball up, it would come back down, and would continue to do that until maybe it came at rest. But he started to lower that inclined plane more and more, and he found once that ball would move down past this, once that ball would roll down the inclined plane, continue to move on this horizontal path, that ball wouldn't stop until it would hit something else. So Galileo believed that it would continue to move forever and ever and ever until something got in its path or in its way. Galileo really coined the term then, or maybe coined the concept, inertia. And inertia is the natural tendency of an object to maintain a state of rest or to remain in uniform motion in a straight line. So thinking about this would be constant velocity. Inertia is an object's nature to resist a change in motion or to resist a change in velocity. And Newton later realized that mass is really a measure of inertia. Mass and inertia really go hand in hand. Mass, Newton thought, was a quantitative measure of inertia, and Newton thought that a more massive object would have more resistance to change motion. So that object would have more inertia. So a more massive object, more resistance to change, so I would consider that to have a lot of inertia. Okay, so based on inertia, Newton came up with his first law of motion. And that is, if an object does not interact with other objects, it is possible to identify a reference frame in which the object has zero acceleration. This is technically Newton's first law of motion. We have not heard it this way. The other way that we're used to hearing it is actually the alternative to Newton's first law of motion. So if an object does not interact with other objects, it is possible to identify a reference frame in which the object has zero acceleration. This is called the law of inertia, and this law of inertia defines a particular type of reference frame. Remember that we talked about frames of reference last chapter when we talked about relative velocity. So in this law, we have stated something called an inertial reference frame, or an inertial frame. And more specifically, we will hear it as an inertial frame of reference. So let's think of, when we think about reference frames or frames of reference, a moving object can be observed from many different numbers of reference frames. So like we said, it depends on where the object or the observer is located and how that person or how that object is moving compared to the frame of reference. So let's think of a puck on an air hockey table, and that air hockey table is on the ground. And let's say that the air hockey table is perfectly smooth, the ground is perfectly smooth, so I have a puck on an air hockey table, and that air hockey table is on the ground. And let's say that that puck is at rest, and I am standing next to that air hockey table, and I'm noticing or I'm observing this puck. And if it's at rest, then there's no horizontal interactions of the puck with any other object. So that puck is at rest. I see that there are no other forces acting on it. And I then would observe it to have zero acceleration because I'm not seeing that it's moving. I see that it's at rest. So I observe it has zero acceleration. In that case, I would consider that to be in an inertial frame of reference. We also have non-inertial frames of reference. And if we have a non-inertial frame of reference, then I'm going to see an acceleration relative to the inertial frame that I'm in. So a non-inertial reference frame would be where I'm seeing some type of acceleration. An inertial frame of reference would be where I'm identifying an object with zero acceleration. Now we can state Newton's first law in an alternative way, and this is the one that's most common. So we also can say that, again, it's still the law of inertia, but Newton's first law in the absence of an unbalanced applied force. So that means when my net force, and again, net is really key here, when my net force is equal to zero, a body at rest will remain at rest, and a body that's already in motion will remain in motion with a constant velocity. And it's super important that we know that that constant velocity is in a straight line. So this is only applying when we're in straight lines. So absence of an unbalanced applied force or net force is equal to zero. Something at rest or an object at rest will stay at rest, or if it's already moving, it's going to continue to move with that constant velocity. So constant speed, constant direction. So if the net force acting on the object is zero, I want you to remember then there's key phrases here. The object will be either at rest or the object will be undergoing constant velocity. Okay, so it will not be accelerating. Okay, thinking about inertia and thinking about Newton's law as being the law of inertia, let's also talk about mass. And mass is just a property of an object. It specifies how much resistance an object can exhibit to a change in its velocity. We can define, masses can be defined in terms of the accelerations that are produced by a given force acting on them. So I have here this m1 over m2 is proportional to an acceleration, the second acceleration over the first acceleration. This is showing that the magnitude of the acceleration acting on an object is inversely proportional to its mass. So let's say, for example, that I'm applying the same force to two masses. So I have maybe mass 1, mass 2. I'm applying some force so I know that they're accelerating. So force is equal, we know, to mass times acceleration. So on the first one, if I apply some force and we call this mass 1, then I'll just say that this is the acceleration for the first mass. And the same force is going to be applied to the second mass. So I have m2 here, and we're going to call its acceleration a2. So if these forces are equal to each other, then I could say m1 times a1, mass of the first one times the acceleration of the first one, is equal to the mass of the second one times the acceleration of the second one. But I want to compare their ratios of acceleration, ratios of mass. So if I do that, I can divide both sides by a1, so I could get my accelerations on the same side. I would get, ultimately, if I do all my math here, m1 over m2 will be equal to a2 over a1. So I can see that I have an inverse relationship between the mass of that first one and the acceleration of that first one. So if I'm applying the same force to two different objects, I can show that their mass and their acceleration are inversely proportional, which is what this is showing right here. Okay, finally, mass versus weight. I think that sometimes we have some maybe misconceptions about mass versus weight. So, mass and weight are two different objects, two different quantities. Weight is going to be equal to not only the mass that an object has, but also an acceleration, and specifically that acceleration for us when we think about weight is 9.80 meters per second squared. So weight is equal to the magnitude of the gravitational force that's exerted on an object. Weight varies with location, whereas mass will not vary with location. So the mass on Earth of an object may be 2 kilograms. If that object went to the moon, it would stay 2 kilograms. But if that object on Earth, if I think about its weight, it may be 180 pounds. And maybe its weight on the moon is roughly 30 pounds. The reason that that changes is because I have to take into consideration that acceleration due to gravity. So mass and weight, 2 different things. We'll just keep that in mind as we're moving on. We are going to start, guys, on Monday with Newton's second law. So if you have any questions about those first slides, post on the blog or email me. If not, then I will see you on Monday. Have a great weekend. Bye.